title was announced already, so I will talk about the Fröhlich polaron. This talk is maybe a bit different in style, maybe from most of the other talks here, in the sense that it's really about mathematics. It's about mathematical theorems on, however, a problem coming from physics. I think it fits the theme of the workshop, certainly, because, well, the problem is really a 20th century problem, but the solution had to wait for the 21st century. So I will talk about some recent results in the direction of the mathematical analysis of the Fröhlich polaron model. So the first slide I can probably skip in this audience, right? So this is sort of a rough sketch of the physical picture of an electron moving through a polarizable medium. That's sort of the concept, the traditional concept of the polaron, and I will talk about what is physics called the large polaron, right, where the electron wavelength is much longer than the lattice spacing. So in the model there is no lattice anymore. One works in the continuum approximation. Okay. So here is the model going back to the work of Fröhlich in the 1930s. So it's just a description of one electron moving through this polarizable medium. So let me just explain the notation. Right? So here is the Fröhlich Hamiltonian. Laplacian, that is just minus the gradient squared. So this is just the kinetic energy of the electron. And for simplicity, I said the bare mass of the electron equal to 1/2, so that the constant in front here is 1 and h bar is 1. So the usual choice of units. And so that's the electron, right? So the electron Hilbert space, the square integrable functions as usual. And then the electron interacts with this phonon field describing the polarization. So that's the bosonic Fock space with the usual creation and annihilation operators, A's and A daggers, right, satisfying the standard commutation relations. Right, and in this Fröhlich model, the dispersion relation for the phonons is simply flat. So this corresponds to sort of completely uncoupled oscillators, right? So choose the unit such that the dispersion relation, the frequency, the energy is just equal to 1, right? So this, in other words, the field energy in the Fröhlich model is just the number operator counting the number of phonons in the system. And the interaction between the electron and the phonon field is given by this 1/k form factor, which physically corresponds to the interaction of a monopole with a dipole, right? So 1/k is the Fourier transform of 1/x squared, which is the interaction potential between a monopole, namely the electron, and the dipole, which is the one that is created by because of the polarization. Okay, and there's one parameter in the model, which is the coupling constant, which is, as usual, written as the square root of alpha here. Okay, as I already said, this is really the model of the large polaron. The lattice spacing is not visible anymore because one works in the continuum approximation. And this is just a comment for maybe the more mathematically minded people. So this interaction looks a bit singular. It looks ultraviolet singular because the 1/k is not square integrable, but the model is really not ultraviolet singular, right? So because of basically the effective smearing that goes on because of the electron kinetic energy, one can check that this Hamiltonian is actually perfectly well defined and it's bounded from below. It just has a bit of a funny domain. So if you ask what is actually the operator domain of this operator, it's not straightforward to characterize, but in practice that doesn't cause any problems. Okay, and this is, of course, you can think of this as also some sort of toy model of quantum field theory. There are many models of this kind in physics. Modeling different physical scenarios, but the mathematical structure of the models is similar. For instance, right, the Nelson model in quantum field theory or things of that kind. Okay, so back to the Fröhlich model. The Fröhlich model has a very special property at large coupling, namely, in some sense, it becomes exactly solvable at large coupling. The large coupling limit turns out to be really something like a classical limit in the sense that this quantum field theory described by the Fröhlich model becomes a classical field theory in the strong coupling limit. And the easiest way to see this is just to appropriately rescale the variables. Basically, at large coupling, the relevant length scale wavelength of the electron is like 1/alpha, so it's natural to rescale all lengths by alpha and rescale the corresponding momenta, right? So if one just makes this change of variables here. Instead of x, you write alpha minus 1x, and instead of the a's, you write this combination of a's. Then the Fröhlich Hamiltonian up to a trivial alpha squared prefactor, which I divide here, becomes formally independent of alpha. The alpha just scales out if you make this change of variable. You get the same Hamiltonian as before, but there's no more alpha apparently. But the alpha is still there. The alpha shows up as an effective Planck's constant in the commutation relation between the creation and annihilation operators of phonons. Right? So the operator formula, the alpha has disappeared, but the alpha is still here as this effective Planck's constant. And now it's quite obvious what you expect to happen if alpha goes to infinity in the strong coupling limit. Effectively, the commutator becomes 0, which is saying that the field operators become commutative, so it becomes a classical field theory. Okay? So, in other words, the strong coupling limit corresponds to a classical approximation where we can think of these a's and a daggers just being functions instead of field operators, right? So these functions, I'll call them maybe z here, right? So to indicate that these are now complex valued functions instead of operators. So instead of ak, I write zk, and it's actually convenient to go back to configuration space and write the z in terms of the Fourier transform, right? Which I split into a real part phi and an imaginary part pi. Okay? So now if you do this and you just rewrite the Fröhlich model here in terms of these variables, what you find is what is known as the Pecha functional. So this is sort of the classical version of the Polaron model. The electron is still quantum, right? So there's an electron wave function psi. So the kinetic energy of the electron is, as usual, the integral of grad psi squared. But now, you see, if you go back here to the field energy, this was just the sum of the oscillator energies, right? So this is now classical, so it's just the integral of phi squared plus pi squared. These are sort of classically the canonical conjugate variables for this oscillator field, phi and pi. And the interaction is, now we're in x space, right? It's this 1 over x squared interaction between sort of the charge density of the electron, psi squared, and the classical field phi. Okay? This is just an identity that you get from the Hamiltonian if you make this approximation replacing the quantum field operators by just functions. Okay, so this is sort of the general Pecha functional, which still involves the electron and it involves the classical polarization field. And now if we look at something like the ground state energy, say, right, so we want to look at the minimal energy of the system. So we minimize with respect to, say, the fields, phi and pi, right? And this is very easy to do because it's quadratic, right? If you minimize, of course, the pi wants to be 0, has no reason not to be 0, and the phi appears quadratically, so you just complete the square, and you find, after minimizing over phi, what is, I think, usually called the Pecha functional. You get, well, the integral psi squared is unaffected, but what you get is this effective Coulomb self-interaction of sort of the electron charge density psi squared with itself. Okay, this just comes from completing the square using the fact that 1 over x squared convolved with itself is 1 over x, and there are some constants 2 and pi also floating around which are suppressed for simplicity of the notation. Okay, so this is the Pecha functional. It has some interesting properties, namely, so this was proved by Lieb in the 70s. So first of all, there exists a minimizer. So now if you want to minimize this over psi, there exists a minimizer, and it's actually unique up to the trivial symmetries of the problem, which is in particular translation invariance. So the minimizer is unique up to translations. Of course, you can put you have a minimizer, but there's no preferred location, so you can put it anywhere you want. So physically, this you can interpret as sort of a self-trapping of the system, right? You have a translation invariant system, yet the electron wants to sit somewhere, right? It's sort of trapped by the potential well it creates, so to say, through the polarization field. At least in this classical approximation, there's this self-trapping which leads to the fact that there is actually a minimizer, a well-localized minimizer of the function. Okay, so this is all sort of well-known things. Let me call the lowest energy, right? So if you minimize this now also over psi, you get a number which I call the Pecha energy. Now, what I would really like to discuss, I'll discuss it on my next slide, sorry. So first thing about actually now validity of this approximation, right? So I told you that this simply this prediction, the classical approximation, comes simply from a formal strong coupling limit where you neglect the commutator. Now actually proving this in precise mathematical terms, giving estimates on the validity of this classical approximation, turns out to be not so straightforward as this, I think, heuristic explanation is that I just gave. In fact, the first proof was given by Donska and Varadan in the early 80s. So proof, I mean that you actually look at the actual ground state energy of the Fröhlich Hamiltonian, but appropriately rescaled, there's this alpha squared factor which I pulled out. And then after that, as in the strong coupling limit, indeed, you get what is predicted by the classical theory, the Pecha approximation. Right, so they proved this in the 80s. Actually, they proved this using Feynman's path integral formulation of the problem, which will not play any role here in my talk, but I think it's interesting on its own right, so I'll just recall it here, that basically Feynman pointed out, right, that if you write the sort of heat semigroup, you take e to the t times the Hamiltonian, then you can actually integrate out the boson field once you go to the path integral representation for the electron, basically because the boson field is quadratic, so you can, it's all just Gaussian integrals, so you can do it, and you get this effective self-interaction of the paths, right? So this is here Wiener measure, so this is just Brownian motion. You have a Brownian motion of an electron that's described by a path omega of t running from 0 to some large number, capital T, and then from integrating out the phonon field, you get this effective retarded Coulomb interaction where the Brownian motion of the electron interacts with itself at some later or earlier time with this exponential weight in the retardation. Okay, so this is well known, and actually, so Donska and Varadan, they're sort of probabilists that they worked with this path measure, and out of that they managed to deduce that indeed, well, first you have to send t to infinity, and then you have to send alpha to infinity, and you have to recover this classical Pecha approximation. Later in '97, there was sort of, I would say, a much simpler proof, and one that doesn't use this description, but just uses sort of inequalities operator techniques, sort of more elementary techniques by Lieb and Thomas to prove actually a quantitative bound on the difference between the quantum ground state energy and its classical approximation, the Pecha energy. The lower bound is of relevance here because the quantum problem always has a lower energy than the classical problem. This is easy to see basically because one can always use coherent states to effectively make the quantum field a classical field, and this will always give you an upper bound to the energy by the variational principle. So of interest is the lower bound, and what they proved is actually that the classical approximation is correct up to errors that are at most as big as alpha to the minus 1/5 as alpha is large. Okay. So this 1/5 is not expected to be optimal. In fact, as I explain in just a minute, one expects here an alpha to the minus 2, and in fact, there's a concrete prediction of what the leading order sort of correction to the classical approximation should be, and this is exactly what I would like to explain here. So this has to do with quantum fluctuations, right? In the sense that the Pecha approximation is really the classical limit where you think of the quantum field taking a definite classical value, but of course it's really quantum, so it fluctuates around this classical value, and these quantum fluctuations will lead to an energy, and that's sort of the leading order correction to the classical approximation. Okay, and this is what I would like to first motivate. It's again not very difficult to see what it should be, and for that it turns out to be useful to look at sort of a different expression for the Pecha energy where you don't minimize over the fields, but actually you rather minimize over the electron, and think of this still as a function of the field. Right? So maybe just quickly let me go back to the Pecha functional, right? It's really a function of still 3 variables, the electron wave function and the classical field and its canonical conjugate, phi and pi, right? And what we did here is we minimized over phi and pi to get a functional of psi, okay? But now let me do it the other way around. Let me first minimize over psi. The pi will still play no role for this in the static problem. That only plays a role in the dynamics. So pi I also minimize, but let me keep the phi fixed, the minimize over psi. So as a function of psi, the functional was just quadratic, right? It's just sort of the usual quantum energy, a Schrödinger operator minus Laplacian plus this effective potential, the potential well created by the polarization field. So this is convolution, right? So this is just phi convolved with 1 over x squared. That's the effective potential that's created by the electron in this classical picture, right? So minimizing over psi is the same thing as saying take the lowest eigenvalue, namely the infimum of the spectrum of this one particle Schrödinger operator minus Laplacian plus this potential. Okay? And the integral phi squared is still there. So this is sort of a Pecha function, the Pecha functional of the polarization field where the electron has been integrated out, the other way around from before, right? And now, of course, if we minimize this over phi, now we get the same as before, right? If we minimize this over phi, we get the Pecha energy. But let's not just minimize, let's actually expand around the minimum. Okay? So there will be a minimizer, I call it phi p for Pecha, right? Actually, there will be many because you have translation invariance, but you just pick one of them, and then you expand to quadratic order around the minimum, so you get some quadratic expression with some explicit quadratic term here, which is simply the Hessian of this functional, right? You just take two derivatives at the minimum point. Okay, so there's an explicit formula for this HP. I didn't display it because it doesn't really play a role here. Okay, so if phi is close to phi p, you just do this quadratic expansion plus higher order terms, which are at least cubic. Right? And this Hessian we know is a positive, right? Because after all, we expand around the minimum, so it has to be positive. You can also check that it's less than 1, simply because the 1 comes from the quadratic term here, and this thing here being the ground state energy of a Schrödinger operator with potential linear in phi has to be a concave function, so its second derivative is negative. So the Hessian is between 0 and 1. Okay? It has 0 modes that come from the translation variance, obviously, right? So the Hessian is not strictly positive, but one can prove that there are only the 0 modes coming from translation invariance. So there are 3 0 modes, and aside from that, the Hessian is strictly positive. So this was proved by Lenzmann, sort of as an extension of Lieb's original work of the uniqueness of the minimizers, going back to the 70s. So now if we take this classical approximation here, if we stop at second order, and now we quantize it again, right? I did the classical approximation, I expanded to quadratic order, and now I quantize the problem. It's just harmonic oscillators because it's quadratic, right? So it's easy to quantize. So what do I get? Then I would get a ground state energy of all these oscillators as an additional shift to the to the Pecha energy, right? So this would lead to the following, what I call a conjecture, right? Which says that the Fröhlich Hamiltonian, its ground state energy, should really be, well, it's the classical Pecha energy to leading order, and then you expect a 1 over alpha squared correction, right? That's the H bar, really in the commutation relations, right? So then H bar omega, that's the oscillator ground state energy. For each mode, you get a 1 over alpha squared correction, and for each mode simply means that, well, you have to take the square root of this Hessian here, right? Because think of this as a harmonic oscillator, it's omega squared times x squared, so omega is the ground state energy, so it's the square root of the Hessian, and there is the -1 simply coming from the ground state energy of sort of the unperturbed problem and the non-interacting problem. So so the prediction would be that the shift in ground state energy between the quantum and the classical problem to leading order in alpha should be 1 over alpha squared, and the coefficient should be the trace of the square root of the Hessian -1. Okay, and one can actually check that this is a trace class operator, meaning that the Hessian is basically 1 plus something that is trace class. Okay, so this makes sense. And this is something one can find in the physics literature. Explicitly, I found it only in some review paper by Alcock in the 60s, but I think it's been known much longer. Actually, if anybody has information on the precise history, I would be curious. I looked at some literature going back to Bogolyubov in the 30s. There's some papers, but only available in Russian, and so I'm not 100% sure. Alcock basically attributes this formula to Bogolyubov already, but I couldn't really find it in the Russian literature, so I don't know precisely what its history is, but it's certainly well known as a conjecture, as a prediction of what the leading quantum contributions should be compared to the classical energy. Okay? I formulate this conjecture also because, right, so I'm mathematically minded, I want to prove things as a theorem. It's still not a theorem, right? Otherwise I would have formulated it as a theorem. Turns out it's still, we don't know quite how to prove this, but we can prove it in a slightly simpler context. this is on my next slide, where we confine the system to some finite volume, right? So I call this a confined polaron. I don't want to take the Fröhlich polaron, which a priori is defined in infinite space. I confine my system to some finite volume, right? I think physically this makes a lot of sense. I mean, you have a finite size sample. The model is still the same. You have to just decide somehow what you do in terms of boundary conditions. Okay, so this is what I call here confined polaron. So it's the same Hamiltonian as before, except that I confine both the electron and the polarization field to some finite volume, which I called omega here. So think of omega as a ball or a cube, whatever your favorite set, but a bounded set in R3. Okay, so the electron is only allowed to move in this bounded set. So its kinetic energy I think of as described by the Dirichlet Laplacian. So in other words, I put Dirichlet boundary conditions, right? The electron wave function is forced to vanish outside this domain omega. And the polarization field, the same thing. I use here configuration space notation. So this is just the number operator written in configuration space, where I just integrate over omega because all the field modes are also confined to this finite size omega. And then the natural coupling function here between the electron and the phonon field would be something like the inverse of the square root of this Dirichlet Laplacian, right, which corresponds exactly to the 1 over k in the infinite volume space. Okay, so if omega were R3, this is exactly the Fröhlich polaron model, and this is sort of just its finite volume generalization, okay, or restriction to finite volume. Okay, and it turns out that in this setting we can actually prove this conjecture. So there's a theorem which was proved jointly with Rupert Frank a bit less than a year ago, where we can establish indeed that if we look at the ground state energy of this Fröhlich Hamiltonian, right, the alpha, again, I recall in this notation, the alpha is not apparent in the Hamiltonian because the alpha is in the commutation relation. 1 over alpha squared is the effective Planck's constant as far as the quantum field is concerned. So the commutator between A and A dagger is 1 over alpha squared. Okay, so now if we look at the large coupling limit, then not surprisingly, right, to leading order, we find the classical approximation, which is just the Pecha functional as before, except that now it looks a bit different simply because everything is confined to this volume omega, but otherwise it's the same classical approximation as before. And the leading order correction we can indeed establish to be the 1 over alpha squared as predicted times this factor, which is the trace of the square root of the Hessian of this Pecha functional minus the identity operator. Okay, and there are error terms here which I didn't specify. I mean, little o just means something that's higher order as alpha goes to infinity. We actually do have upper and lower bounds, some explicit exponents in terms of alpha. Okay. I should add one thing here, namely there is sort of an assumption about omega. So I told you that in R3, right, Lieb has proved that the Pecha functional has a unique minimizer up to translations. And now once we break translation invariance because we confine the system to some finite volume, we would expect that generically now there should be a unique minimizer, right? Somehow the electron would sit somewhere close to the center of whatever this domain is. But it turns out that that's actually rather difficult to prove. We don't have a general proof of that. So it enters as an assumption here that there is a unique minimizer of this Pecha functional and sort of a strictly positive Hessian close to this minimizer. This is an assumption we can prove for a ball. This is a joint work with my student Dario Feliciangeli, also from last year. But for a general domain, we can't actually prove that, so it enters as an assumption here for this theorem. Okay, so maybe I'll just say a few words about ideas in the proof, or even why it's difficult, right? So maybe it's not even that obvious. Why is it even difficult? Because I think at least I hope that I gave sort of simple, convincing arguments why this should be true. It's just a quadratic approximation. You quantize, that's the formula you get. So why is it difficult? Well, basically, the problem comes from the infinitely many modes that you have. This is really a quantum field theory problem, right? So there are infinitely many oscillators involved, right? And if you go back to maybe I'll switch back just for a second, to the approximation here where I said, well, let's assume the classical field configuration phi is actually close to the classical minimum, this phi p, right? So then you see there's an error term which I neglected. So I have to argue that to make this precise, I have to argue that the classical field is in some sense, the quantum field, which is now a fluctuating object, right, is in some sense always close to its classical value. Okay? But what I want to say now is that strictly speaking, it never is, right? Because there are infinitely many directions in which it can differ, right? If you have infinitely many oscillators and each one oscillates a bit, then the sum of all these oscillators is always infinite. Right? So in practical terms, if you apply this to the quantum problem, this term is never small. In fact, it's always infinite, simply because there are infinitely many directions in which the quantum field phi can differ from its classical value. Okay? So that's sort of the main technical obstacle, that if you want to think of phi as being the quantum field, right, which is now a fluctuating object, it's never close to its classical value. In fact, it's not even square integrable, because there are infinitely many directions in which it fluctuates. So if you want to make this precise, you first have to introduce somehow an ultraviolet cutoff to make sure you want to decouple the high momentum modes from the system. They shouldn't play a role after all. This is all sort of low momentum phenomenon. But to quantify the error you make in making such a cutoff, that's sort of the hard analysis. That's where you have to work. And that's tricky, because you see any kind of approximation you make, any kind of cutoff, will already affect the leading term in the energy. So whatever you do, you have to do a very precise analysis to make sure that whatever manipulation you make in the system, it should sort of only affect the energy over here. But if you make an error here, right, it better be a very small error. Okay, so this is just sort of an indication why it's difficult. It's basically there are infinitely many modes involved, so the classical approximation is sort of has to be taken with a grain of salt. Okay, I will not maybe go into the details here. If anybody's interested, I'll of course be happy to explain later some of the details going into this. Let me just say one thing which should be clear maybe from this discussion. Why does the confinement help? Right? I told you that I can't quite prove this yet in infinite space. Why does the confinement help? Well, simply because once I have an ultraviolet cutoff and I'm in finite volume, then I have only finitely many modes. Right? And that's what I want to get to. I'm saying for finitely many modes, this is sort of easy. I have to get to a setting where I can neglect all but finitely many modes. If I'm in finite volume and I do an ultraviolet cutoff, I have finitely many modes. If I'm in infinite volume, I still have sort of the infrared problem to deal with, and that we yet cannot control sort of well enough to be able to extend this theorem to the infinite volume case. Okay, so but now maybe I'll leave it at that. I want to switch gears a little bit and talk about a second result concerning the effective mass. So this now goes back to the infinite volume case, right? So forget about the confinement again. I go back to the original Fröhlich model, which is defined in the infinite space, and in particular, it's translation invariant, right? So as such, it has a conserved quantity, which is the total momentum of the three conserved quantities, right? So the Fröhlich Hamiltonian, in the infinite volume, it's translation invariant, so it commutes with the three components of the total momentum, which is the sum of the electron momentum and the field momentum. Right? So as such, I can now talk about the joint spectrum, the joint energy momentum spectrum as usual. So mathematically, one says there's a fiber integral decomposition, but never mind about that. The point is that I can talk about the energy as a function of momentum, because I can go into the sector of a fixed total momentum and can ask what is the lowest energy there. Right? That's what I call E of P. It's the lowest energy, the Fröhlich Hamiltonian, constrained to have total momentum P. Okay? And there's an explicit representation of this effective Hamiltonian with total momentum P, which is simply obtained by plugging in, instead of the electron momentum, you write the total momentum minus the field momentum, and then you have a Hamiltonian that only depends on the Fock space variables. There's no more electron, right? So this is, I think, called the Lilo-Pines transformation. Okay, but in any case, we have an energy as a function of momentum, and we can use this to define the effective mass of the electron, right? I told you I work in units where the bare mass is 1/2, but the effective mass of the electron, as far as its dynamics is concerned, is larger because the electron dresses itself with this cloud of phonons, right? That's this whole concept of a polaron. So we expect that the effective mass is strictly larger than 1/2, and so the effective mass can be defined simply by looking at the energy as a function of momentum and looking at its curvature at momentum 0. Right? So we look at the energy difference for the moving electron with momentum p and its rest energy at momentum 0, right? So we have to look at this difference. This is expected to grow like p squared, right? And the coefficient in front of the p squared we call 1 over twice the mass, as usual. So this is the definition of the effective mass. You just take this difference of the energies, you divide by p squared. For small p, this number is called the effective mass. Now, actually, there has been a lot of investigations on this property, also on sort of mathematical terms, but it turns out that it's rather difficult to get any precise information or precise estimates on this quantity, in particular in the large coupling limit. And the reason, in some sense, you could simply say is from the fact that this is an energy difference, right? So we somehow understand the energy reasonably well in the strong coupling limit, but now we have to look at an energy difference, right? So if we know the energy only up to a small error, it's not going to help us to know an energy difference, right? Because we first have to send p to 0, and then we have to ask what happens for large alpha. If you go back to Pecha, then there is actually a concrete prediction based on this classical approximation on how large this effective mass should be. In particular, it's expected to diverge as alpha goes to infinity. In fact, there's a precise prediction on that it should diverge like the 4th power of alpha. And this diverging has to do exactly with this self-trapping that I mentioned before. Right? In the classical limit, the electron really just sits there. It's trapped by its own, by the potential well it's created by by the polarization field. So an electron just sitting there obviously corresponds to an infinite mass. Right? So in the classical approximation, the effective mass is really infinite. So we expect that for the quantum problem, the effective mass will diverge as will diverge in the strong coupling limit. This has certainly been always expected, but actually it was proved only very recently, the joint paper with Elliott-Leib from earlier this year, where we finally managed to actually prove this, namely to take this effective mass defined here and actually show that in the strong coupling limit, it indeed diverges to infinity. Maybe I'll spend the last couple of minutes to just give you some idea about the proof of this, because it's actually quite easy, it turns out, or well, yeah, in retrospect, it was quite easy, and it's motivated from the Pecha picture. Namely, at the end, it's a variational calculation, right? But you see, you have to be careful. I go back one slide once more. As I said, because you have an energy difference, right? If I want to prove that the mass goes to infinity, I have to prove that the inverse mass, I'll take 2 minutes, yeah. I have to prove that this inverse mass, right, goes to 0, so I need an upper bound on this expression. So you can say the variational principle, right, I want an upper bound and the energy is a function of p, but the upper bound has to be sharp as p goes to 0, right, because I first have to tend p to 0, so whatever upper bound I get, it has to coincide with the unknown quantity, the actual ground state's energy of the Fröhlich Hamiltonian. Right, as p goes to 0. So whatever I do in my ansatz, I better have to take sort of the exact ground state, so to say, at momentum 0, which I don't know. That's sort of the complication. But even if we don't know it, we can still sort of, we know its existence, so to say. So in this fiber picture, there is a ground state of the actual Hamiltonian at restricted to total momentum 0. We don't know what it is, but we know it exists. We know some properties of it, and we can use it now, modify it to put in some momentum into system, so to say. And the modification is simply motivated by the Pecha ansatz. So the Pecha approximation, you can, on the level of states, means that you think of the whole system as being in a product state, totally uncorrelated, the electron and the phonon field, and the phonon field being in a coherent state, a classical state, right? So that means if you go back to momentum space, that means that you expect your wave function, momentum space, to look something like this. Here is the electron wave function, that's the minimizer of the Pecha functional, as a function of the electron momentum, which I now plug in the total momentum minus the field momentum. And this is just the coherent state for the field. Okay, so this is sort of the Pecha approximation. But now I just expand this in P to leading order. I take the first order term, and instead of writing the 0th order term here, I write here the exact ground state, whatever it is. So the Pecha ansatz motivates this kind of ansatz where phi 0 is the exact ground state at momentum 0, and you make this ansatz for the state of the system at momentum p. And it turns out that works. Okay, so you plug that in, you do the calculation. You have to, of course, prove the appropriate properties of the ground state here, that so to be able to evaluate the corresponding expectation values. But that's sort of where the work is. We managed to do that and then show that indeed, using this trial state for the variational principle, we can show that this 1 over twice the mass indeed goes to 0 as alpha goes to infinity. So time is up. Let me just conclude. Quick summary. What I talked about was, on the one hand, quantum corrections, right, to the classical Pecha approximation of the Fröhlich polaron as far as the ground state energy is concerned, and the divergence of the effective mass of this electron of the polaron in the strong coupling limit. Okay, maybe open problems I already mentioned, so let me not even go through this. Let me, the last point, just say that there's a corresponding time-dependent problem, right? So this was all about the ground state. Somehow one would also like to know that the corresponding dynamical problem, so if you actually look at the dynamics of a polaron, you can, for strong coupling, approximate it reasonably well by the corresponding classical dynamics, which is simply the dynamics generated by this sort of classical Pecha functional, which I can think of as a classical dynamical system. And this leads to the Landau-Pecha equations describing the classical evolution of such a system, and there's current work in progress understanding indeed the validity of these Landau-Pecha equations to approximate the dynamics given by the Schrödinger equation in terms of the Fröhlich Hamiltonian. Thank you. Well, so depends. So a priori not, in the sense that it's fixed and alpha goes to infinity. You see, so there's of course two length scales involved, so to say. So I'm fixing one, send the other to infinity. Now, if you want the quantitative estimates, then the constraint is sort of in here, if you want. This is a theorem which holds for fixed omega, but now I think one thing. Or I rephrase your question, you can ask, how does this depend on omega, right? So if the domain now becomes big, then our error estimates become rather bad. They are explicit. I could sort of in principle display them, which leads to the fact that there is some possible, so the result is sort of uniform in the size of omega, but only up to a limit, in the sense that, say, the size of the system could depend on alpha, but only a little bit. So as long as you keep it fixed and send alpha to infinity, there's no problem. But at the end, you want sort of quantitative error terms, and there, of course, you're not completely uniform. If you were, then we could extend the theorem to the infinite volume case.
So may I ask a very simple and stupid question? So how should I think in physical terms of these quantum fluctuation corrections? There is any picture I can make with respect to the Pecha model?
Yeah, so my picture simply is, so the Pecha basically tells you if you want the average value of this polarization field. After all, it's a quantum field. So Pecha tells you what its average value is, but the quantum, right, it's a quantum field, so it really fluctuates. So this describes the fluctuations around the classical value, which is somehow its expectation value. Yeah. Yeah, but this is.
If you look at what happens in computations, actually, it never happens spontaneously.
Yeah, so
there were papers, we also published papers talking about fluctuations, which are required in order to, let's say, produce this. So you have some vibrations which come together and produce some precipitation side for polarization. So is it included in this theory?
So I think the question is about the self-trapping, I think, if I understand correctly. So the self-trapping is an artifact of the classical approximation. For the actual quantum problem, there's never self-trapping, because the effective mass might be large, but it's not infinite. So the self-trapping is really an artifact of the classical approximation. So I think one way maybe to interpret this is that the quantum fluctuations indeed kill the self-trapping. So there is, after all, always sort of some kind of quantum tunneling, so the electron will never actually self-trap. So that means, in particular, if you go back to the Fröhlich Hamiltonian, right, the Fröhlich Hamiltonian does not have a ground state. It's translation invariant. The electron will never sit somewhere. So this is an artifact of the classical approximation. Oh, sure, of course. So you can, of course, confine the electron by whatever means and then ask for its dynamics. How long will it take to spread out and things? Yeah, so all of this. But here I'm talking sort of about the statics. I'm really talking about the ground state. And I'm saying the quantum problem never has a ground state, whereas the classical one has. And that's because in the classical one, effectively, the effective mass is already infinite. So you have this self-trapping. But as soon as the coupling is finite, you never strictly have self-trapping. Yeah, so this is about the ground state energy of the Polaron model.
Yeah, so how does it compare to the original Pecha solution and the final solution? If I replace this the Hamiltonian inside and I estimate the energy, what do you get?
Sorry, I don't quite understand the question. So this is the Pecha energy. That's what you get from the classical picture. That's the quantum problem, and I'm exactly interested in the difference.
Yeah, I guess I'm asking what is numerically, what is the second bit?
Oh, the numerical value of this? Yeah. I don't know. It's some number. I don't know.
So the Pecha expression is a well-known energy.
Oh, yeah. So this is of course also some. Okay, maybe we'll go back to the unconfined case. Right? This is a certain number which is probably known to any precision you want. I mean, people can compute this numerically, and in the same way they can compute this number numerically. It's just some number. I don't know what it is because personally I don't care. But of course. No, but you see, the fraction is given by alpha. So for me, that's what's important. Of course, if you say you have a concrete physical problem, alpha is 2, then you really care about what these numbers are, right? So I'm saying they are probably known. I mean, this one is certainly known to a high precision. This one, I don't actually know how precisely people have computed it. It's probably non-trivial because this Hessian, even though there's an explicit formula, you don't have a spectral representation. So computing this trace of a square root is probably not easy in practice. So I don't know how well the numerical value of this number is known, but what is important for the ratio, what is important for me is there is an alpha squared, and I think of alpha as being very large, right? So that separates the scale. This is a large alpha.
Can you say anything about what happens to the causing particle rate of the state phi 0, which you don't know? So is there a causing particle actually in your proof for alpha to infinity? So if you would calculate what is the residue of your state phi 0, which unfortunately in proof you don't know, to define the causing particle, I would like to define the causing particle weight z weight. So can you say anything about that?
The short answer is no, because I don't really understand the question. So you
can calculate the overlap of the non-interacting state
mm-hmm.
with the interacting state. This gives you what I would call a causing particle weight.
I see. Mm-hmm. Yeah. Yeah. It will be 0. It will be 0. In fact, it will be exponentially small in alpha. This state is very different from the non-interacting one. I mean, first of all, the non-interacting one is just the vacuum, right? So if I go, sorry, I think you're talking about this fiber picture, right? So we're talking about the ground state of this Hamiltonian, say, at p equals 0. So if there's no coupling, the ground state is the vacuum. The actual ground state for large alpha will be very different. In fact, the overlap with the vacuum will be exponentially small in alpha. I'm not saying I can't prove this, but maybe I could even. But I'm not sure. If you tell me it's an interesting question, I'll think about it. But it will be very small. The point is that for large coupling, the state will be very different from the non-interacting one. For small coupling, I guess you can compute it using perturbation theory. But sorry, for the? I think even for the coherent state, if you take alpha to infinity, the overlap will go to 0. Yeah, that's what I'm talking about. Yeah. Yeah.
Yes, one small question.
Very small, yes.
It's interesting about a connection of those results, inverse results to the old numeric results. For example, when Miyake for the ground technology. If you calculate numerically, I think it will be confirmed.
This is numerical computation of this number you're talking about. I think that's Miyake, right? Yeah.
I mean the classical.
Yeah, so that's the classical number. I think that's the Miyake people refer to is a numerical value of this number. Yeah. Yes.
Will be confirmed, I expect.
I mean, I'm saying it is this number. I mean, Miyake computed this number. I'm just saying from a mathematical perspective, I don't care what its value is. It is what it is. But it's, of course, perfectly consistent because we're talking about the same number. It's just whether you want, just all I'm saying is I don't really care about the numerical value of this number, but we're talking about the same number. Yeah.
So I think we can deal with Miyake.
These are sort of separate questions, but I have no reason to doubt the calculation. Yeah.